Okay, let's see how we can derive the kinetic energy equation for an ideal gas. Kinetic energy equals to 3 over 2 n kT, which is required in the learning of this topic. So we have with us a system, a cube measuring length L, breadth L, and height L. So I have here represented in 2 dimensions, so L by L. And let's say we have an ideal gas moving from one side of the container to the other side with the speed u in 1 dimension, and the mass of this particle is m. So what is the change in momentum experienced by this one particle as it travels from one side to the next and then back? So the change in momentum will be final momentum subtract initial momentum. The particle with mass m and speed u, final momentum mu, initial momentum will be negative mu. So change in momentum would be mu minus m negative u, will be 2mu. Recall Newton's second law. The net force is equals to change in momentum divided by change in time. So expressing it in this way, what is this change in time? It will be the time taken for the particle to move across the container and then back. So the time taken would be the distance traveled divided by the speed of the particle. So we have here the speed of the particle u, distance traveled is 2l, to and fro, and the time taken is delta t, and therefore delta t is equals to 2l over u. Substitute into the equation for force, we get 2mu over 2l over u. Rearranging, we get mu squared over l. Right. Now imagine there are a large number of particles, n number of particles, and each carrying its unique speed u1, u2, u3 all the way to un. And therefore with these unique speeds, we have its individual unique forces that each particle will carry as it bounces off the walls, F1, F2, F3 all the way to Fn. Let's introduce a new term that we deal with, average. We are aware of average speed. Now we are going to introduce this term known as average speed square. So let's say we have this symbol u square with the parenthesis, so we call this mean square speed. And with this mean square speed, I can use it to average out the force by one particle would then be expressed as m over l times mean square speed. Instead of the speed unique to only one particle, now I have a general expression that represents the force exerted by all the particles, and therefore the total force by n number of particles would then use multiply by n. Now we are only still talking about 1 dimension. If I have a 3-dimensional system, the force applied in 1 dimension would then have to average out in 3 dimensions, which is 1/3. So in 1 dimension, the force would be n over 3, m mean square speed divided by l. Further on, let's express this in the context of pressure. So we know pressure is force over area. So total pressure exerted on one side of the wall is total force on that one side, 1 dimension, divided by the area of the wall, which is L times L. So we have here the expression in this way. So we know L times L, this is the area, multiplied by another L, which becomes the volume. So we can bring L cubed across and re-express it as volume V. So the whole expression becomes like that. So total kinetic energy, we know, is half mv squared. total would be multiplied by the number of particles, where m refers to the mass of one particle and n refers to the total number of particles, and u square parenthesis represents mean square speed. So rearranging, we get total kinetic energy is equals to half n times m mean square speed, which actually equals to 3 PV. And rearranging, we get 3/2 PV. Now recall, PV is actually an expression of the ideal gas, equals to NKT. So we can express it in this way. And therefore, the average kinetic energy will then be divided the whole total kinetic energy by the number of particles there. So each particle will have this amount of kinetic energy. And dividing by n, we get 3/2 kT.